We're going to do one more video on friction because I think we need it. And we're going to do a couple of harder problems. And that's good because this will be good review for the quiz. So what we've got here is a large box on the floor. And it has two people moving it. One is going to be pushing the box. That's a pretty rough hand. And the other person is going to be pulling the box. They have a rope on it. So there's two forces on the box. Uh-oh, and it looks like there's some friction. The free body diagram is going to be really critical for this problem. So mg goes down, normal goes up. We've actually got two forces that are trying to push the box forward. Even the person pushing is going in the same direction as the person pulling. So there's two forces trying to move that box to the right, and fighting them every step of the way is friction. So A asks us to calculate the force of friction. The nice thing in this problem is that it's at a constant velocity. We really like constant velocity problems because then the sum of the forces is 0. The forces going forward are the 236.1 from the push and the 89.3 from the pull. Friction resists. So since this is all equal to 0, we can just bring the friction over and add those two numbers together. And we get a force of friction is 325 newtons. So that's not too bad. Now C says the mu k is 0.35. Calculate the mass. Friction is mu k times the normal. In this case, the normal goes up, the mg goes down. So we're safe saying that the mg has to exactly balance the normal force. So friction is mu k times mg. Oh, we want the mass. Let's divide both sides by mu kg. So mass will be the force of friction over mu k times gravity. 325. Now let's see what mu k is, 0.35, so it's a pretty rough floor. And 9.8. Now 0.35 is really close to a third. And 9.8 is really close to 10. So it would be like we're taking 325 divided by 10, which is somewhere in the ballpark of 100. And I get a mass of 94.9 kilograms, which is pretty close to 100, so I believe that number. Now, if one box is fun, wouldn't two boxes be even funner? So let's see what's going on here. A 50 kilogram box is sitting next to a 5.0 kilograms, not 50, is sitting next to a 2.5 kilogram box. And we're going to push on it. There's our hands pretty roughly. But it says there's friction here. There's static friction here. And I wanted to do this problem because I thought it was important. It not only addresses friction, it addresses the contact force. We're not touching the 2.5 kilogram box. The only thing that can move it forward is contact. And for every force, there's an equal and opposite force, so that 2.5 kilogram box will push back on the 5 kilogram. So we've got to do some free body diagrams. Let's do it for the 5 kilogram box. mg goes down, and we have to assume it's sitting on a floor or a table, so normal goes up. We are pushing. Friction will resist. It says we just want to get the box moving, so that's static. But there's another force resisting on the big box. Can you see what it is? It's the contact force. So this is for the 5 kilogram box, the big box. Now let's take a look at the smaller box. mg goes down, and I'm going to use lowercase m and uppercase M for the big box, and normal goes up. There is no push on the little box. The little box is only moving because it's in contact with the big box. But there's still friction. They're sitting on the same table. A nice thing here is we want the minimum force to just get it moving. So let's look at the big box, the 5 kilogram. The sum of the forces in the x direction will be 0. So 0 equals the force of the push minus friction minus the contact force. We don't know the force of the push. Friction is mu s times the normal, which in this case is mg, minus c. Okay, we know mu s is 0.45. It's a 5 kilogram box times 9.8 minus c. So that's just going to get us some number. And I know we're going to need to go into another slide here so it doesn't get too crowded in a moment. Times 9.8. That's 22. We'll make it 22.1 minus c. Let's move that over. And we're stuck. We can't move forward anymore in this problem because that's where we got. We've got two variables. So let me write that on the next slide. 22.1 is force of pull minus contact. Now for the 2.5 kilogram box, some of the forces will be 0 in the x direction. There's no push on that box. There's only a contact force. And resisting it is mu s times mg. Remember, this is the normal force. So let's double check our mu s, 0.45. So we can start, sorry about that, minus, we can start putting our numbers in here. 0.45, the mass of the box is 2.5 kilograms times 9.8. Oh, this is really nice because we can just get the contact force when we multiply those out. .0 newtons. Hey, we solved part of the problem. Now using systems of equations, and we're not going to need to stack them in this case, we'll just substitute. We know what the contact force is. It's 11. So I'm going to add 11 to both sides. So I substituted for C, then I just got to get it by itself. And the force of the push should be 33.1 newtons. And now the moment of truth, which is a little scary since I'm recording. I'm doing all this live. Let's see, 33.1, 11 newtons, and we solved the problem.